Alright, chemistry. We're back at it after some snow days. I mean, Syracuse in March, February. Syracuse in Syracuse in the winter. What are you expecting? Um, I said the first thing I wanted to do was go over this. Then I'll talk about some lab questions, and yeah, that's actually pretty much it. Talk about this, and we'll talk about the lab questions. So setting these up, um, you should just be using this equation, again, from the reference table. Make sure to use Kelvin for your temperatures, because if you don't, you can end up with like 0 in the denominator, and that's just not a thing that can happen. So alright, here we go. Sample of carbon dioxide has a volume of 3.5 liters at 125 kPa. So V1 is 3.5 liters, P1 is 125 kPa. What pressure? P2 is what we don't know, and V2 is 2 liters. Alright, so we didn't mention temperature, which means it doesn't matter, / it would be the same on both sides, so it would cancel out. So mathematically we don't need to worry about it. So the way that I had to set up would just be P1 V1 equals P2 V2. So 125 kPa times 3.5 liters should equal P2 times 2 liters. There we go. And if I do this math really quickly, sorry, possible mistake there. Let's do this. There we go. 125 times 3.5. One thing that I will note, divided by 2, that happened a few times during class, be careful when you're actually writing down numbers that you know that this is like 3.5 and this is 2.00. Because it can be easy to try to do this math and then do 125 times 350 divided by 2. It's like 350. That's a very different number. So if you do this, P2 should equal 218.75 kPa. That's our pressure. If I was being very exact, which I will ask you to do in the future, I should round this to the appropriate number of sig figs. This has 3 sig figs. This has 3 sig figs. This has 3 sig figs. My answer should have 3 sig figs, so 219 kPa. If I was being very exact. Don't forget about sig figs. They will probably be what we round to. Rather than me telling you, okay, round to the ones place for this one, or round to the hundreds for this one, round to sig figs. It'll almost always be like 3. 3 sig figs is very typical, which we'll see soon. But let's keep going. Number 3, we have a sample of propane. Occupies 250 liters. That's a volume. 125 kPa pressure. 38 degrees Celsius as temperature. Here's a new pressure. Here's a new temperature. So those are 2's. These are all 1's. Find the volume. So I have 125 kPa times 250 liters over 38 degrees Celsius is not okay. We need to convert it to Kelvin. That's 303, 313. No. Sorry. 303, 311 Kelvin. Add 273. I don't trust my mental math right now. 273 plus 38. Yeah, 311. That equals 100 kPa times V2 divided by 95 degrees Celsius, which turns out to be 368 Kelvin. Now you can do math with the Celsius numbers, and in this case you'd get an answer. Unfortunately, it would not be a correct answer because of how the Celsius scale works. You can heat something up from a negative temperature to a positive temperature, and if you tried that here, and you had a negative temperature on this side and a positive temperature on this side, you would never get them to equal each other. Like, that would just be impossible. So we use Kelvin because there's no 0, because there are no negatives. And now, doing the math, 125 times 250, 311, should get that V2 equals 369.7749 liters. Okay, our units for volume are liters. But if I look, I know that this temperature here and this temperature here only have 2 sig figs, but when we convert them to Kelvin, they have 3 sig figs. So 3 sig figs is the least. I need to round to this spot here, which means that it's going to be 370 with a decimal place liters. That's what it would be rounded to sig figs. Number 4, we have a I don't want to cross it out. I just want to underline it. We have a pressure. That's P1, and then we're changing the pressure. Okay, so this is P2, and this is the changed volume. This is asking for the original volume. So I'm actually asking for V1 here. So 1.18 atmospheres times V1 equals 1.5 atmospheres times 250 milliliters. And again, doing some math. V1, if I look at this, this has 3 sig figs. This has 2 sig figs. This has 3 sig figs. Doing multiplication and division, so I need to round to the lowest number of sig figs, meaning I need just 2. So 1.5 is 250. This is going to be 317.79. Oh, just kidding. That should be a 9. There we go. 996 milliliters. I have to convert that to 2 sig figs, which is going to be 320 milliliters. That one's a little weird. I need to go to this spot here, which means I'm going to use the 7 to round up. No decimal place. That way this is actually 2 sig figs. Finally, number 5, the volume of a gas. So I have a volume, I have a temperature, I have a pressure. Find its volume at STP. Now, here's where I need to kind of give you a little asterisk, because I said before, way back here, if you see STP, 273 Kelvin, 1 atmosphere, I should have been more clear, and I apologize for this. If you see STP, check table A, and use the units that you're given. You're given units of Kelvin and kilopascals, kPa. So the pressure is 92.1 kPa times 200.0 milliliters over 2. That is the worst fraction in the history of fractions. We're going to clean this up. We're going to clean all of it up. Eventually we're going to clean all of it up. There we go. Alright, we're cleaning it up now. 92.1 kPa times 200 milliliters over 275 Kelvin. There's all my initial conditions. Those are all my 1s. My 2s at STP. kPa STP, kilopascal STP, is 101.3 kPa. I don't know the volume, that's V2, and I'm dividing by temperature in Kelvin is 273. So if I'm solving for V2, and I'm doing some math, that means I got 92.1 times 200 divided by 275. Alright, that means I get 180.5136 blah 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 blah. Nope, yeah, milliliters. Okay. So my units here are milliliters. If I look at my numbers, I see 3 sig figs, and I see 3 sig figs. That's the lowest. Nothing has 2 sig figs. We need to round this to 3. That's 181 milliliters. Right. I don't think that the actual math is all that difficult. It is just making sure that you set it up appropriately. The setup is the tough part. This is a multiple choice question. The reason I am rounding to sig figs here is because in multiple choice questions, they will be rounded to sig figs. So you'll see answers. You might see an answer for something like number 4 that the answer is 320, right? One of the listed answers is 320, even though you calculated 317, and the reason for that is because of sig figs. So I just wanted to show you that. The only other thing that I wanted to mention today was talking about the questions from the lab. So the version that I did with the Can Crush, my program isn't responding. We'll give it a second. There we go. Okay. The initial volume was 355 milliliters. That's like a standard soda can. The initial temperature was 273 Kelvin, because that's zero, or no, sorry, that's wrong. The initial temperature was 373 Kelvin, because it's a boiling point of water in Kelvin. Boiling point of water is 100 Celsius. Convert to Kelvin, you add 273. The second volume is what I wanted you to solve for, and the second temperature was the freezing point of water, which is 0 Celsius, which is, again, why you can't do that. The pressure in the room remained the same, the actual outside of the room. The inside of the can actually changed, but we'll talk about that in a couple questions. So if I was setting this up, I would have 355 milliliters divided by 373 Kelvin, and I would say that that equals X over 273 Kelvin. And by doing that math, you would end up with the answer. That's going to be the new volume. That should be the new volume of the inside of your can. The second question I asked was, why was there more water that I poured out of the can, or that you poured out of the can, compared to what you put in? Because I said put in like the tiniest bit of water, right? The reason for that is as that can crushed, right? It was this big and then it crushed up to be smaller. As it crushed up, it actually created a little like vacuum effect. And it sucked up some of the water that was in that snow water, that ice water that I put it in. So the reason it had more water in it is because it created a suction effect. It drew in water from the ice water, so that as it was being crushed. The last question I asked, and it ties into the first question, the other question I asked. I only asked 2 questions here. It was a very quick lab. The second question I asked was in terms of pressure. So like I actually wanted you to use pressure. Why did the can crush, right? And it's the opposite effect. One day, my whiteboard program will respond the first time. But it's the opposite effect of this, right? You throw a gas can into a fire, the gas on the inside is moving faster, so it exerts more pressure out than the outside can push in, and because of that, the can explodes. In our case, because we cooled the temperature so rapidly, what we did was we made the pressure on the inside much lower than 1 atmosphere. So because we slowed down the particles, they were not hitting the walls of the inside of the can as much. The pressure on the outside of the can was always 1 atmosphere. That was just the pressure of the room. But inside it was lower than 1 atmosphere. So as the gas particles outside were pushing and pushing and hitting the outside of the can, they realized, hey, we're winning this fight. Let's just keep winning. Bang, 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 bang. But it all happened so fast because it's a lot of particles. So what you saw and what you heard, that thwomp, that crush, was from the air particles outside, the pressure of the air particles outside overcoming the pressure from inside. So in terms of pressure, the pressure of the gas particles inside the can was lower than outside the can. So the can crushed on itself because of the pressure difference. All right. Something for C-Day. We are actually going to do another lab. This one is in the lab manual. It's another straightforward one, but y'all need to check out a video, right, before you try the lab, before you look at the lab questions. Fully remote students, there will be another lab video that will go up. But hybrid students, I mean, like, really everybody, right? I'm going to go through page 52 here, because the bottom page 52 is kind of like the topic for the lab. I just want you to have this little background information before we go through it. If you don't understand everything here fully, it's not that big of a deal. I will talk about it as we do the lab. Another note that I'd like to make on E-Day, E1 day, really, the day before break, which should be Friday. I do want to have a quiz on just the gas information, and right up to using this equation and the bottom of this page. So from page 47 to 52. There are examples here on 53, and there are examples obviously on page 51 that we haven't done that you can do for practice. But I'd like to quiz on that on Friday. Just want to let you know. I want to do, I wanted to do 3 labs before the break, but I'll do 2 labs and a quiz. It'll be about the same number of points. But yeah, until the next video, or until I see you in class next, take care of yourself. Be good, kids.